Hello everyone, I am Aniruddha from IIT Indore. Today we are meeting for the 12th time in this course on measure and integration by NPTEL, and today is the last live discussion session. Today it will be mostly about Fubini's theorem and its applications to check whether a given function is in L1 or not in the product space. And of course, today we will try to solve as many doubts as possible of the participants. So if any online participants have any questions, please ask them right now. I'll give you 2 or 3 minutes. Then we'll begin with today's discussion. So, okay. So if there are no questions, let us let us begin. So I want to discuss a few examples where we can check whether a function on the product space is L1 or not using the Fubini's theorem. So notice that what was the Fubini's theorem? Let me just write it. Yeah, it's thick, I think. Yeah. So what it says is, suppose f from x cross y to r is a measurable function. And then, that satisfies any one of the following. That satisfies any one of the following. So the first condition is that f is non-negative. That means at every point x comma y in x cross y, f of xy is a non-negative real number, or f is L1 x cross y in the product measure, or integral of x, integral of y, mod of f of xy, d mu y, d mu x. This is finite, or integral of y, integral of x, mod of f of xy, d mu x, d mu y. This is finite. So notice that, okay. Yeah, let me not write it directly. So if any one of these conditions is satisfied, then change back the color. Yeah. Then we claim that f is in actually L1 x cross y, and integral of f of xy over x cross y with respect to the product measure mu cross nu. This is same as, first let us integrate with respect to y, then with respect to x, f of xy, d mu y, d mu x, or let us first integrate with respect to x, then with respect to y, f of xy, d mu x, d mu y. Okay. So notice that with this we can actually see that the last three conditions are just the same. Right? Very pure. Because if f is in L1, then mod f is integrable because it is a non-negative measurable function, and then middle term is finite, so the other two terms are also finite. If third one is true, then the last term is finite, so middle term is finite. And if the fourth is true, then the first one is finite, so the middle one is finite. So in all these cases, each of them implies the other. In fact, yeah. So for a non-negative measurable function, let us look at some remarks. One, f non-negative is an L1 function on x cross y if and only if integral x integral y f of x y. Oh yeah, actually I did not mean to write here. Yeah, then these things happen. Right. So integral x integral y f of x y d mu y d mu x. This is finite, and this is if and only if integral y integral x f of x y d mu x d mu y is finite. And of course, inherently L1 function, it means it is same as saying integral over x cross y f of xy d mu cross mu of xy. This is finite, right? So the Fubini theorem tells us this, that if we have a non-negative measurable function, then to check whether it is an integrable function on the product space, it is enough to check one of the two iterated integrals. And if any of them is finite, then all the three are finite and they are equal. Secondly, if integral of x, integral of y, f of xy d mu y d mu x, this is not equal to integral over y, integral over x, f of xy d mu x d mu y, then f cannot be in L1. Okay? Because if f was in L1 x cross y, then automatically these three things must be equal, right? In particular, the last two must be equal. So if the last two are not equal to each other, then none of these conditions can be. In particular, f cannot be in L1 x cross y. Okay, so we are going to use some of these very simple remarks that follow from the Fubini theorem to check whether a given function is actually in the L1 space of the product space or not. So to do that, let us start with some very basic examples. So first, which example should we take? So suppose I take x and y both are closed interval 0, 1. Their corresponding sigma algebras are both the Borel sigma algebra of 0, 1. Oh yes, and one more thing, one must assume here that all these spaces, so of course we need measure spaces for this, right? That x a mu and y b mu, they are well sigma finite measure spaces. That is what we require. Measure spaces. And then we can construct x cross y, a cross b, mu cross b. This is the product measure space. With all this construction, only we can state the Fubini theorem. Okay, now let us go back to our example that we want to see. So here both my spaces are 0, 1. Both the sigma algebras are the Borel sigma algebra of 0, 1. And both the measures are the Lebesgue measure. And I wish to define my function f from x cross y to, well, r as follows. F of xy is 1 whenever x is a rational number, and it is 2y whenever y is not a rational number and x is not a rational number. So, well, one can ask what happens when x is a rational but y is not a rational. So in that case, it has to be 1 because this is not satisfied. So this is satisfied when both the things are satisfied. So if x is a rational number, then this thing is not satisfied. Similarly, if y is a rational number, then this thing is not satisfied. So perhaps I should write or y is a any of this. It is 1, otherwise it is 2y. So one cannot draw the graph of it. It is rational set has some different values, that irrational set has some different values. But what one can say is surely this, that if we consider this square 0 1 cross 0 1, and if I take a rational line, well, if this is x and this is a rational number, then on this line f of xy is 1. Similarly, if I take y and this is again a rational number, then on this line f of xy is 1. So on what points f of xy is not 1? That is, well, when both x and y are irrational, then at that point it is 2y. So the height is basically 2y. Now, what can we say about its integrability? So whether it is integrable or not. One can check the measurability, it is not a big deal. So let us check whether it is integrable or not. So to do that, as I have mentioned here, since it is a non-negative function, let us observe it, that f is non-negative for every x. Because either it is 1 or it is 2y, and y is a non-negative real number, so f is a non-negative function. Then it is L1 if and only if one of the two iterated integrals is finite. So in particular, let us look at this iterated integral. Since both the spaces are same, it doesn't matter whether x cross y and y cross x basically are same. But still, one of the things to write is going to be easy. So let us write f of xy d nu y d mu x. So inside, in the inner integral, so if I only look at this, x is constant. X is constant for this integral. And there are only two possibilities for this x, that either x is a rational number or x is an irrational number, and both the things cannot hold together. Because an element cannot be inside the set and outside the set together. So for this, what we will do is, right. So either x is rational or x is irrational. If x is rational, then f of xy is going to be 1. Or if x is not a rational number, if it is irrational, then f of xy is going to be 2y. So I can split this whole integral into two parts. Basically, we are going to split the outer integral, this thing, into two parts. When x is a rational number between 0, 1, and when x is not a rational number between 0, 1. So it becomes integral rational numbers intersection 0, 1, integration 0, 1, 1 d nu y d mu x, plus integral irrational numbers intersection 0, 1, integral 0, 1, 2y d nu y d mu x. So if one notices, the inner integral in both the cases is 1. So evaluate this is 1, because actually it is what? It is, well, the measure of, the length of the interval 0, 1, which is 1. And in this case, it is a Riemann integrable function. So Lebesgue integration and Riemann integration are same. So this is y square by 2 on 0, 1. Oh yeah, it is 2 times y square by 2 on 0, 1, which is 1. Right? So both the cases, this is 1. And then basically what we get is, this is integral rational numbers intersection 0, 1 d mu x, plus irrational numbers intersection 0, 1 d mu x. But that is equal to integration of integration over 0, 1 d mu x, that is 1. And 1 is clearly finite. So therefore, this function f is actually an L1 function on 0, 1 cross 0, 1. And moreover, one can say that the integral of f over this product space of xy, this is also 1 because one of the iterative integrals is 1. Now one could have done the other way around also, integrating this first with respect to x, then with respect to y, and one expects that one. Hello, yeah, it is fine. So in this case, both my species are -1 to 1 closed intervals, and both the sigma algebras are again the Borel sigma algebras of -1 to 1. And here also, both the measures mu and nu, they are Lebesgue measures. Let us define a map f from x cross y to r as follows. F of xy is xy over x square plus y square whole square whenever xy is not 0, 0, and when it is 0, it is 0. Xy is 0, 0. So notice that f is continuous almost everywhere because the only point of problem is 0, 0. And to check that this is actually the case, we see that if we take, well, for the path y is equal to 0, because, okay, how to get the continuity also, that is a point, right? That if I want to check the continuity at this point, then what I want to do is, along every path that reaches this point, I want to take the limit. So one of the paths is x equal to 0, another path is y equal to 0. So along this, I want to take the limit. Something like this path could also be possible, or perhaps even a spiral path is possible. So, along every path, we require that the limit must be same and it should be the value of the function at that point. So for this path y equal to 0, that means the x-axis. Let us again look at it. So along this line is y equal to 0. So let us reach 0, 0, either from the right or from the left. Let us see what happens. So we have f of x, 0. This is always 0, right? Because, well, once y is equal to 0, then the above thing is 0. And if x is also equal to 0, then by definition it is 0. So therefore, limit x going to 0, f of x 0, this is 0, which in this case it is f of 0, 0. But if I take the path y is equal to x, then let us see what happens. F of xy, or rather I should, once y is equal to x, one can write f of xx. F of xx is x square over 2x square whole square whenever x is non-zero and 0 otherwise. So if I want to write it, it is 1 over 4x square when x is non-zero and it is 0 otherwise. So now we are taking this path, either coming from the right or from the left. It doesn't matter because it is even function. So whether you come from top or below, right, left, everything is same. So in this case, limit x going to 0, f of xx, and of course x non-zero, this is plus infinity. Because as x goes to 0, 1 over x square shoots up, and which is not f of 0, 0. Therefore, f is not continuous at xy equal to 0, 0. But for any xy which is non-zero, f is a rational function. Rational function. And what do we mean by a rational function? It is. It means that it is the sort of division of polynomials, right? Division of one polynomial by other. It is the quotient of non-zero polynomials. So rational functions are already continuous. In fact, they are smooth whenever the denominator is non-zero. So then f is continuous everywhere except at 0, 0. Or in the terms of measure theory, f is continuous almost everywhere. So let me just go above. Here also, see how can we write this set? Let me give you a hint. All those points in R2 such that either x is rational or y is rational. Right? So, yeah. So notice that this is not Q cross Q. Okay. So we cannot really say that f is equal to 2y almost everywhere. That is, f is not equal to 2y almost everywhere. So we have to think how this is Borel measurable. You can think about it. It is not a difficult task, but still, you have to give some idea. At least what one can say is this is continuous at irrational points, perhaps, or some are in some grid it is continuous. In other parts it is not continuous, and that other part is of measure 0. That kind of an argument one can give. Let us come back. So here f is continuous almost everywhere, and therefore f is Borel measurable. That's one measurable. Okay. But this is not this is not a non-negative function. Again, here I must make an observation. F is not a non-negative function. So to know whether it is in L1 or not, what I want to do is I want to check whether well, now I cannot use this remark which I given before that one of these two integrals is finite implies f is in L1. No. So let us do one thing. Nonetheless, let us evaluate it. The two iterative integrals. Let us see whether the value comes out to be the same. So now, how does one go about it? Yes, let us write it. So minus 1 to 1, minus 1 to 1, f of xy, d mu x, d mu y. Let us calculate this. So this is again minus 1 to 1, minus 1 to 1, xy over, yes, xy over x square plus y square whole square, d mu x, d mu y. Except for, well, when the denominator is non-zero. So for when y is equal to 0, x cannot be 0. X equal to 0, y cannot be 0. So that is the case. But anyway, we can think of integrating it this way because removing one point doesn't matter. So this, what I am going to do is, I want to evaluate this. Let us try to write this inner function as some derivative so that we can use the fundamental theorem of calculus. So xy over x square plus y square whole square, I can write it as minus y by 2 derivative of 1 over x square plus y square with respect to x. Also, I can write this as minus x by 2 derivative of 1 over x square plus y square with respect to y. And one can easily check that they are equal. Because once you take the derivative, is minus 1 over x square plus y square into 2x. So 2 goes away, minus minus cancels, and what remains is xy. So in our case, minus 1 to 1, minus 1 to 1, f of xy d mu x, d mu y, this is minus 1 to 1, minus y by 2, minus 1 to 1, the derivative of 1 over x square plus y square with respect to x, d mu x, d mu y. Again, since for a fixed y, this is a Riemann integrable function on -1 to 1. Therefore, yeah, for a fixed y non-zero, of course. So I can write it as -1 to 1, y is not equal to 0. Maybe I shouldn't write it like this. Just -1 to 1 difference 0, minus y by 2, and then x cannot be 0, so -1 to 1 difference 0, derivative of 1 over x square plus y square, d mu x d mu y. So I am just removing one point from the integral. It doesn't matter. The value is still the same. This is -1 to 1 difference 0, minus y by 2. And now I can use the fundamental theorem to get as 1 over x square plus y square from -1 to 1 d mu y. But this is an even function. Okay? The inner part is even function. Implies that if I substitute 1, it is 1 over 1 plus y square. If I substitute -1, it is still 1 over 1 plus y square, which is 0. Okay? So minus y by 2 into 0, that is 0. Also, integral -1 to 1, integral -1 to 1, f of xy, d mu y d mu x. This is also 0, since f is symmetric with respect to x and y. Symmetric with respect to xy. That is what I want to say is f of xy is same as f of yx. Whatever we have done above for x, just do the same thing for y, and then we'll get. Okay, so we have established the following. We have established that the two iterated integrals, either we integrate x first and then we integrate y, or let us integrate y first and then x. D mu y, d mu x, they are equal. So now the question is, can we conclude from here that f is in L1? Well, from here we cannot conclude. From the above equality, we cannot conclude. And that is because, f is not non-negative, so we cannot say anything about it. So let us try to see whether that is the case, whether we have this thing inside L1. So to do this, let us look at -1 to 1, -1 to 1, mod of f of xy, d mu x, d mu y. Or maybe I want to do the other thing. It doesn't matter because it is symmetric, but still. So d mu y, d mu x. So notice that since mod f is non-negative, this is equal to integral -1 1 cross -1 1 mod f of xy d mu cross mu xy. This I know, this is true. So let us evaluate this iterated integral -1 to 1 -1 to 1 mod x mod y upon mod of x square plus y square whole square. But that is just x square plus y square whole square, because it is already a non-negative quantity. D mu y, d mu x. Now what I can do is, since mod is an even function, I can just write the whole thing as maybe, okay. Let me just write mod x outside. Mod y from -1 to 0, it is still same as from 0 to 1. So it is integral 0 to 1, 2 times y over x square plus y square whole square. D mu x, d mu y, d mu x. So we can do that. So from here to here, how did we go? That is because mod y over x square plus y square on 0 1, this is equal to, well, not this way. how to write it in the proper way. So it is like it is -1 to 0 something plus integral 0 to 1 something, but these two integrals are same. So I am just doing it 2 times the same integral. This is a standard technique in Riemann integration. -1 to 1 mod x. Now what is this? This is actually derivative of 1 over x square plus y square. So it is 1 over x square plus y square on 0, 1 d mu x, which is further -1 to 1 mod x over 1 plus x square minus mod x over x square d mu x. So for one time I put y equal to 1, the other time I put y equal to 0. So we get this. Now again, the thing is here the same thing, that mod x over x square. So I can write it as 2 times integral 0 to 1 x over 1 plus x square minus x over x square, which is 1 over x d mu x. Okay. So now there are a couple of things to observe. First is that integral 0 to 1 over x dx, this is plus infinity, as we have discussed in one of the sessions. Using simple function technique. That is to say, 1 over x is not in L1x here. L1x. But second thing to observe is that integral x over 1 plus x square d mu x on 0 to 1. This is, or rather, if I just multiply 2 here, then it is a derivative. Okay. 2x over 1 plus x square. This is 1 over 1 plus x square from 0 to 1 using the fundamental theorem of calculus. And it is half minus 1, which is minus 1. Yeah. Now there is some issue. What is the thing? Oh, yes. Even here, I think I missed a minus sign somewhere. Because the derivative of this is minus, so here there should be a minus. Or right now, 2y over x square plus y square. So they will differentiate it. Yes, it should come with a minus sign. So here there is a minus sign. Here outside again there is a minus sign. Minus 2 times. So if I start with a negative sign here, then everything is negative. So it is plus 1. Plus half. Yeah, so this is finite. And this is a non-negative function. Therefore, 2x over 1 plus x square, this is actually in L1x, which means x over 1 plus x square is in L1x. Now, we know that L1x is a vector space. Is a vector space. If x over 1 plus x square minus 1 over x, this is in L1x, then 1 over x I can always write as x over 1 plus x square minus x over 1 plus x square minus 1 over x. So I am adding and subtracting the same term, so it doesn't matter. This must be inside L1x, right? So, but that is not the case, which is not the case. This we know to be false. Therefore, this cannot be true. Now, since this cannot be true, what does it mean? It means that this whole integral, this whole integral is infinite. Therefore, integral of minus 1 1 cross minus 1 1 mod f of x y d mu cross mu xy, which is minus 1 to 1 minus 1 to 1 mod f of xy d mu x, d mu y, or we have considered the other way around, d mu y, d mu x. This is plus infinity. Therefore, our f is not in L1 x cross y. So this example establishes the following. So why is this important? Important observation that there are non-negative, there are functions that are not non-negative such that integral over x, integral over y, f of xy d mu x d mu y, this is equal to integral y integral x, f of xy d mu y d mu x, but f is not in L1 x cross y. So in this case, we cannot talk about the integration of f over x cross y. In this case, we cannot say much about, in fact, we cannot say anything about integral over x cross y of f of x. This is one of the important observations. In fact, a standard counter example for whatever we have discussed. Okay. Now let us move on to one more example, perhaps the last for today. That would give us the essence of the Fubini theorem altogether. So why are we doing all this? Is because there are some important remarks that I made. That if something is non-negative, then it is an L1 function if and only if one of the two iterated integrals are finite. And if the two iterated integrals are not finite, then f is definitely not L1. Right? So we have seen the first one throughout, that under the assumption f is non-negative, we have seen that one of these becoming finite makes f L1. And if we drop the assumption that f is non-negative, then this may not be true. We have seen that these two integrals are equal, they are very well finite, but f is not an L1 function. That is what we have seen. Now, just for this remark too, let us see one thing. Let's look at an example. So again here, the spaces are x is 0, 1. The sigma algebra is the Borel sigma algebra of 0, 1. The measure is the Lebesgue measure. The other space is 1 to infinity. The sigma is again, here the sigma algebra is the Lebesgue sigma algebra of 1 to infinity. And the measure is Lebesgue measure. We'll see the sigma algebra won't matter. We could have considered the Borel sigma algebra as well, and still we would have got the same thing. And then let us define the function f from x cross y to r as f of xy equal to e to the power minus xy minus 2 e to the power minus 2xy. Okay. So again, to look at this in a proper way, we have to look at, sorry, excuse me. Okay. To look at, so this function is, if I just ask someone to integrate this from minus 0, 1 and 1 to infinity, f of xy d mu y d mu x, or 1 to infinity 0 to 1 f of xy d mu x d mu y, then they are quite difficult to handle directly. Quite difficult to handle directly. So what one can do is, see, this looks almost like the derivative, right? Because e to the power minus xy minus 2 e to the power minus xy I can write as 1 over x, well, should I write it 1 over x? Yes, or perhaps I should write minus 1 over x. Minus 1 over x into minus x e to the power minus xy plus minus 2x e to the power minus 2xy. Okay. This remains minus because I require a minus sign again. So it is minus minus plus, but then another minus. So overall it is minus. Whenever x is non-zero, of course. If x is 0, that happens only in one case. We can remove that point. No worries. Which is clearly minus 1 over x, derivative of e to the power minus xy, minus derivative of e to the power minus 2xy. So all in all, this whole thing is minus 1 over x, derivative of e to the power minus xy minus e to the power minus 2xy. So this is one thing to observe. Another thing to observe is I can also write it in terms of y, minus 2 to the power minus xy, because it is again symmetric in y, symmetric in xy rather. So it is minus 1 over y, derivative with respect to x, e to the power minus xy minus e to the power minus 2xy. And notice that y is never 0. So I can write it without any worries. Okay, so now let us compute it, because now one can hope to do it nicely in the sense, well, to be using the fundamental theorem of calculus and all. So integral 0 to 1, integral 1 to infinity, f of xy d nu y d mu x. This is equal to integral 0 to 1, integral 1 to infinity. Let us see what it is. So first I want to integrate respect to y. So let me use equation 1 here. So it is minus 1 over x del by del y e to the power minus xy minus e to the power minus 2xy d nu y d mu x. But for the inner integral, x is constant, so that can come outside. So it is 0 to 1 minus 1 over x, and by the fundamental theorem of calculus, this is e to the power minus xy minus e to the power minus 2xy from 1 to infinity. Now, as y goes to infinity, both these terms goes to 0. So nothing remains. And as y goes to 1, what happens is it becomes 1 over x e to the power minus x minus e to the power minus 2x. So all in all, what one can write? Oh, and with a negative sign. So this negative sign goes away. So 0 to 1 e to the power minus x into 1 minus e to the power minus x upon x d mu x. So let us keep this in mind. So this is our equation 3. Now, integral 1 to infinity, integral 0 to 1, f of xy, d mu x, d nu y. Let us try to calculate this. Again, using equation 2, this is minus 1 over y, derivative of something. It is minus 1 over y, integral 0 to 1, derivative of e to the power minus xy minus e to the power minus 2xy, d mu x, d nu y. And then using a similar technique, minus 1 over y, e to the power minus xy minus e to the power minus 2xy from 0 to 1, d nu y. But this time it is not really 0. So at 1 we have something. So it is minus 1 over y of e to the power minus y minus e to the power minus 2y minus at 0, what will it be? It is e to the power 0 minus e to the power 0. So it is 1 minus 1. Well, the overall sum is 0. But yeah, none of the terms are 0. It is 0. This is 1 to infinity minus e to the power minus y minus e to the power minus 2y. Or maybe I'll write it in that way. So minus 1 to infinity e to the power minus y into 1 minus e to the power minus y over y dy, d nu y. So, well, notice that equation 3 and equation 4 are same, except for the fact that the variables are changed, and of course the domain is changed. So, I can very well write this. This is equal to minus integral 1 to infinity e to the power minus x, 1 minus e to the power minus x upon x d nu x by a simple change of variables. Change of variables from y to x. So that we can do because it is just a matter of writing. Whether I write y or whether I write x, that is the same thing. The function matters. Inside function is same. Okay. Now, the question is whether the left hand sides are equal. Are these two equal? If they were equal, then the difference must be 0. So let us try to calculate the difference. So integral 0 to 1, integral 1 to infinity, f of xy d nu y d nu x minus integral 1 to infinity, integral 0 to 1, f of xy d mu x d mu y. So from equation, what was it, 3, we have integral 0 to 1 of some function, integral 0 to 1 e to the power minus x, 1 minus e to the power minus x upon x d mu x, minus minus plus integral 1 to infinity e to the power minus x, 1 minus e to the power minus x upon x d nu x. But notice that this and this, they are both Lebesgue measures. Both are Lebesgue measures. And these two, they are improper integrals, right? Improper Riemann integrals. So we can use the properties of that. We can combine the two sets, and 0 to 1, 1 to infinity together gives us 0 to infinity. So this is 0 to infinity e to the power minus x, 1 minus e to the power minus x upon x d mu x, where this is of course the Lebesgue measure on 0 infinity. Okay, so open 0 because division by x, that is not very suitable. We can extract upon it. Now, notice that for x positive, e to the power minus x is positive, and 1 minus e to the power minus x, this is also positive. Yeah, correct. Although one must argue why. Minus x would be negative, e to the power minus x would be less than 1, and therefore 1 minus e to the power minus x is bigger than 0. So their product is bigger than 0. And hence the integral is bigger than 0. E to the power minus x, 1 minus e to the power minus x upon x, d mu x, this is positive. That is to say, the difference of the two iterated integrals, integral 0 to 1 f of x, integral 1 to infinity f of xy d mu y d mu x, and 1 to infinity 0 to 1 f of xy d mu x d mu y, this is non-zero. Or what is the same? These two iterated integrals are not the same. xy d mu y d mu x, this is not equal to 1 to infinity 0 to 1 f of xy d mu x d mu y, and hence f is not an L1 function. Therefore, f is not an L1. Because if it was by Fubini's theorem, these two have to be equal, and they have to be equal to the integral on the product space. So again, in this case as well, we cannot talk much about. In fact, we cannot talk anything about this integral of f of x, right, on the product space x cross y. So, all right. So with this, like we complete the whole essence of Fubini's theorem and all the possibilities that one can have. Before ending this session, I would just like to mention here a few things that Fubini's theorem is applicable in very few cases. First of all, we require the two major spaces to be sigma finite. That itself is a very big thing to ask for. In fact, there are a lot of examples of major spaces which are not sigma finite. For instance, one of the simplest example is the counting measure on R, which is not a sigma finite measure. So there we cannot use the Fubini's theorem. Similarly, Fubini's theorem can be applied if any one of these holds. Now, f is non-negative is again too much to ask for because most of the functions that we would deal with, they may not be non-negative. In fact, they could be oscillatory or even the nice functions for us, for example, sine, cosine, and other things, they are not non-negative, right? But still on finite intervals they are integrable and all. The other thing is f is in L1 or any of these, they are equivalent statements. So even this is too much to ask. Out of many functions that you may encounter, those functions may not be in L1. So directly, we cannot use the iterated integrals to calculate the integral of this over the measure space. So that is one thing to take away from all this. Okay. This is applicable in only a few situations. So for instance, to give an example, I think 1 over root x. Yeah, we have seen examples, right? Most of the times we cannot use it. Okay. So again, I'll give you a minute or two to ask questions. Then we will stop. So are there any questions from YouTube audience? Can put it in the live chat. Okay, so if there are no questions, let us stop. And now we will not have any more live sessions. If you have any doubts before your exam, you can contact me through mail. Most of the times I am active on mail and I'll try to reply as soon as possible. And we'll meet perhaps next semester if there is a rerun of this course or some other course. Otherwise, all the best for your exams. Thank you.